you will learn to use the regression analysis to predict the values of dependent and independent variables, the meaning of the coefficients, how to estimate these coefficients in case of simple as well as multilinear regression. And then we will also make inferences about the slope and the correlation coefficient. And finally, we will look at the statistical significance using the F test and the T test. So let us recall by a few concepts that you have already seen in the PCA LDA session, which was taken by Professor Bala. So he defined the covariance as given in this formula, and the covariance. What does it mean? If the value of covariance is greater than 0, then both your variables x and y tend to increase together. That is the positive correlation. If covariance, sorry, if the covariance is negative, that implies that if one variable is increasing, the other will decrease, or vice versa. So this is a kind of inverse correlation. And if your covariance is 0, that means there is no linear relation. So it does not necessarily mean, actually, if there is the covariance is 0, it doesn't really mean that there is no complete statistical independence. So that we will see in a while. So here your xi and yi are the individual data points from the variables x and y, and x bar and y bar are the averages of the variables x and y. And n is the number of paired data points. So this formula calculates how much two variables change together. Okay. Next, we have something called as correlation, which is the division of covariance by the standard deviations. So here, sigma x and sigma y are the standard deviations of x and y. Covariance was unbounded, but correlation is lying between, the value is always lying between -1 and 1. It has no unit, it is unitless, dimensionless, whereas your covariance is dependent on the variable's units. This correlation is easy to interpret, whereas covariance a bit harder to interpret. Standardization is used in correlation, and this basically correlation is compares the strengths of the relationships. So to sum it up, covariance tells you the direction of the relationship, and correlation tells you the direction and strength, and is easier to interpret because it is standardized. That's what we saw in the previous lectures. But when it comes to the questions like how much weight increases for every extra centimeter of height, this cannot be answered using these two terms. Questions like, are height and weight correlated? These type of questions may be answered using these two concepts that we just saw. So for example, if you take the example of analyzing study hours and exam scores. So correlation, what it does is it measures if the student who studies more tend to get higher scores. Okay, so that correlation coefficient will be higher, and it will indicate a strong positive relation. But using this, you cannot give the prediction. It is just the summary of the relation. But regression, what will regression do? It will find an equation between these two variables, that is study hours and exam scores, and then it will it will give us an equation which will be helpful in predicting the score using the study hours. So use of regression is when we want to predict one variable from the another. So what are these two variables, or these variables in this entire process? The variables are dependent and independent variables. So as students of maths, we clearly know what are these dependent and independent variables. In this case, dependent variable is the variable that we want to we want to predict. Okay, the there may be one independent variable, there may be multiple independent variables. Okay, before going further into the mathematics of the linear regression, let us see some kind of types of relation. So this graph is showing a linear relation. So you can see that as x increases, y also is increasing at a steady rate. So for example, again, the study hours and the exam scores, the more you study, the higher scores you get. Similarly, the bottom graph is also showing a kind of linear relation, but in a negative way. So as your x is increasing, y decreases steadily. So, for example, maybe the number of absents and the grades. If you are more absent in the class, your grades will fall. The next set of relations are the curvilinear relations. So this is an inverted U-shaped relation. So here you can see that y increases with x up to a point and then it decreases. So for example, it may be stress level and the performance. So some stress is good, it helps, it increases your performance, but at one point, if it is more, then it hurts. Okay, so that is, it decreases the performance. This graph is again a curvilinear graph, which is very similar to exponential or power like growth, where when y increases slowly at first and then rapidly as your x increases. For example, the spread of the virus, and the number of infections. More relations, we have more types of relations. So these relations basically are illustrating the different strengths between the variables, so based on how closely the data points follow this line. So here you can see the strong relationships, that is a positive strong relationship in this graph, and negative strong relation in this graph. So, positive strong relation may be height and arm length. So, taller people generally have longer arm length. Negative may be distance from the city center and the property price. So, if the property is farther than the city, then the price also is cheaper. These are some of the weak relationships, positive weak relation and the negative weak relation. So here y tends to increase with x, but the pattern is too noisy. For example, exercise time and the mood score. So there is some correlation between exercise time and the mood score, but lots of variation. Negative weak relation, that means y is decreasing as your x is increasing, but the link is very weak. For example, age and the say amount of social media use. So older age might reduce use, but not strongly. So these are the kind of linear weak relation. Then there are no relationships at all. That is, changes in x do not affect y. Data is random. So, for example, shoe size and the IQ, they are not related at all. There is no relation at all. So these were the some kind of types of relations with I mean we with which we come across in our daily life. So what is linear in mathematical terms? So this equation, all of you know it from our 12th standard. Y is equal to mx plus b. So this tells, this is the equation of a linear line, line segment or line. So here slope is m, which tells us how steep the line is and how the y, that is the dependent variable, changes as x increases. Okay, so mathematically, we express it as rise over run. So m is actually the change in y divided by the change in x. So with this background, we define the regression, simple regression model. So here you see the simple regression model, which is having the dependent variable yi, which is equal to beta naught plus beta 1 xi plus epsilon I. So yi is your uh, dependent variable, xi is the independent variable, this is your intercept, and this is the slope coefficient, and this is the random error term. So this random error term is included to account for variability in the yi, in the dependent variable, that you cannot explain by this linear relationship with xi. So in real world data, what happens is not all the outcomes are perfectly predicted by a single independent variable, or for that matter, multiple independent variable. The error term captures everything else that affects the dependent variable, but is not explicitly modeled. So what I mean by this is that, for example, if there are two students, both studying for 5 hours, so I'm coming back to that study time and the score example. So if two students both are studying for 5 hours, one might score 85 and the other might score 75. This is possible, right? So this difference could be, we cannot actually explain this difference exclusively with the study hour of 5 hours for both of them. So this difference could be due to sleep quality, exam anxiety, prior knowledge, or classroom participation, or anything else. So all these unexplained influences are taken care by this error term. Okay, so that is why you have this error term in the linear regression model. So this is the error term that you see here that accounts for the unexplained factors which cannot be modeled explicitly. This is the regression line that best fits this data, and you also have an intercept, that is beta naught, and you have the line, best fit line, which models your dependent variable y and independent variable x. Okay, so there are some assumptions that linear regression model follows. So first assumption is linearity. So as the name suggests, it is linear regression model. So the relation between the dependent and independent variable is linear. That means the changes in dependent variable follow those in the independent variables in a linear fashion. So this assumption is very, very important. If your data is not following this assumption, then you may not be able to apply this linear regression model. Next assumption is of the independence. That is, the observations in your data set are independent of each other. Okay, that means the value of the dependent variable for one observation does not depend on the value of the dependent variable for another observation. So they are independent. That means if you're recording something for one person, it is not affecting the recording for the other person. Next assumption is homoscedasticity. That means across all levels of independent variables, the variance of errors is constant. That means that amount of independent variables has no impact on the variance of the errors. So this is also a very, very important assumption. If this doesn't hold, then you cannot really apply this model, and the method which is following will not be correct to model that data. Then you have normality, that is errors in the model are normally distributed. That is, if you plot the distribution, plot the errors of every instance with that of predicted, it should follow a normal distribution. Then finally, there is no multicollinearity. That is, there is no high correlation between the independent variables. We will see an example also of this. So this indicates that there is a little or no correlation between the independent variables. Only those will contribute to your model, which have no correlation between the independent variables. So we will see such an example numerically after we see the multiple linear regression. Okay, so this is the simple linear regression mathematically, where you have your yi cap is equal to b naught b beta naught or b naught plus beta 1 xi, and and by now you know that this is your dependent variable and this is your independent variable. This is b naught is the intercept and b1 is the slope. So the entire problem is to estimate these two. Now let us see how to estimate the coefficients. So first of all, you have to draw a sample from the population. So you begin with the population, but since it's often too big or too large to analyze that entire population, you will have to take the sample. For example, if you are studying how study hours affect the exam scores in a university, you cannot collect the samples from all the students of the university. So you collect the data from a sample of say 100 students. Then calculating the sample statistics. So using the sample data, you compute the statistics such as the means of the independent variable and the dependent variable, the covariance between them, the variance. These are necessary to estimate the slope and the intercept of the regression line. Okay, so there may be many lines that can represent the linear relationship in the data. So how to choose the best line, that is uh, how to produce this straight line will be the focus of our next session now. So the best fitting line is drawn through the scatter plot of the sample data, and this line is called the least squares regression line. So what it does is, I mean, how do we get this best fitting line? By minimizing the sum of squared errors, also called as residuals, that is the vertical distance between the actual data points and the line. So the basic idea and the main idea of linear regression is that we have to minimize the sum of squared errors or the residuals, that is the vertical distance between the actual data point and the line. And this line then represents our model that is given by yi hat is equal to b naught plus b1 xi, where yi hat is the predicted value of y. So what is residual? So a residual, as I said, that it is the vertical distance between the actual data point and the line. So it is basically the difference between the observed value that you have in your data set and the value predicted by the regression line. So sum of squared residuals is actually the total of all the squared errors, okay, between the observed data and the regression line. So each error is squared to make all values positive so that negatives don't cancel out each other, penalize the larger errors more heavily, and linear regression basically uses least squares to determine this. So you can see that we can have multiple of these, and for every line you find the residuals, and you find the line that minimizes these residuals, that is you choose the slope and the intercept so that the total squared area between the actual and the predicted value is as small as possible. So basically, this is also an optimization problem where we are trying to minimize this sum of the squared errors or the residuals. Okay, so this way you get the best fitting line. So this is basically an intuition behind it. We will look at it mathematically very soon. So this, as I said, that this is an optimization problem. In this graph, you can see that when the sum of the squared residuals change with the orientation of the line. So we choose that line for which the sum of the squared is minimum of all. So this is how the best fitting line is obtained by choosing the minimized value of sum of the squared. So this will give us an intercept and a slope. So now let us look at mathematically how to estimate these regression uh, mm, uh, estimate the parameters in this regression line. So we use the least square method, which is very standard uh, in regression analysis, but I will come to its disadvantages in a while. So the it will find the best line by minimizing the sum of squared of residuals that we graphically we saw. So what we have to do is we have to minimize the sum of the squared errors, that is the difference between the observed value and the predicted value, sum them up for every instance, and then you minimize it. So basically this is an optimization problem which we will see how to solve. So the least squares regression line looks like this, and it will give us an intercept and a slope. Okay. So what do they mean? I mean, intercept basically, as we all know as students of mathematics, it is the estimated value of the independent variable when the value of dependent variable is 0. And what does the slope mean? It is the change in the mean value of the independent variable for every unit change in the value of the dependent, an independent variable. Okay, so now we define mathematically what do you mean by residual sum of squares. So error is defined as the difference between the observed and the predicted value. This is the ith residual for ith observation. The sum is squared when you square e, that is the error, for every instance, and then you sum it up to get the residual sum. And then, I mean, you can replace your predicted yi from this equation to be yi minus b not cap minus b1 cap xi. So you can replace every ei with this equation, and you will get an equivalent equation for residual sum of squares. This we have to minimize. So this RSS, that is the residual sum of square, is the total squared error between all actual values and their predicted value. So this is what we want to minimize to find the best fitting line. And how do we do that? We use the least square estimation for now. So the least square method finds these two parameters, that is your b naught and your b1. Okay, it finds these parameters for which the RSS value is minimum. Okay, so these formulas, as you can see here, these are basically derived from calculus. So as mathematics students, we all know that how to find the critical points. So that is what do we do? We take the first derivative, take the first since this is a multivariable problem, so you what do? You take the partial derivatives of the RSS with respect to b naught cap and b1 cap. You take the partial derivatives with respect to b naught cap and b1 cap and set them to 0. Okay, so when you do that, what you get? You get the value for b1 cap. Okay, so mathematically, if you want, I can write it down for you. So is my screen visible?
Yes, ma'am.
Okay.
Yes, ma'am, it is visible, ma'am.
So this is how you can take the first derivative of, a partial derivative of RSS with respect to B naught cap. Okay. And then you set this equal to 0. So this will give us summation I is equal to 1 to n yi minus beta naught uh, beta naught cap minus b1 cap xi is equal to 0. Now we set the partial derivative with respect to b1 to 0. So that is del RSS with respect to del b1 cap to 0, and we will get summation I is equal to 1 to n xi. Okay, you have, because you have xi here, yi minus b naught cap minus b1 cap xi equal to 0. So if you look at the RSS equation here, once we have partially differentiated with respect to beta naught cap, b naught cap, and set it equal to 0, and once we have partially differentiated with respect to b1 cap and set it to 0. So you get this. And then you have to solve these two equations. Solve the system of equations. So from here, you can substitute. You can open up this summation and you can find the value of b naught. So which will be, so this will give us b naught cap is equal to, so this will be summation yi will be y bar, and other term will be b1 x bar. So this will be b1 cap x bar, because summation xi will be x bar. So this is how you get b naught cap. This you substitute in the second equation. So you get put b naught is equal to yi minus b1 cap x bar in the above. So we get summation xi yi minus y bar minus b1 cap x bar summation xi minus b1 bar summation xi square is equal to 0. So this is xi yi, okay, minus, instead of b naught I have put y bar minus b1 cap x bar, and you have summation xi with this also, and minus summation xi square b1 cap. So that is as it is. So when you simplify this to find the value of b1 cap, you will get, you just have to rearrange the terms. So you will get what you'll get whatever is what we got here. So that is this term, you'll get this term. Okay, yi minus y divided by summation xi minus x bar the whole square. So this is how you get the slope. That is, this is the closed form solution for your slope. And once you have the slope from the equation of from this equation, you can get b naught. That is y bar minus. You can get the b naught, which we already have found here. Y bar minus b1. Once you have b1 bar, you can just put it in b naught and get the intercept also. Okay, so this is how the closed form solutions are obtained for finding the estimation of parameters using least squares. Okay, for finding the slope and the intercept. Similarly, in the multiple regression case, so in the multiple regression case, what happens is you will have more than one independent variables. So in this case, we have taken p independent variables, and when we have p independent variables, your uh, regression equation becomes yi is equal to beta naught plus beta 1 xi1 plus beta 2 xi2, etc., plus beta p xip, plus the error term, which accounts for the unexplained factors, where your yi is basically the observed outcome for the ith data point. Okay, you will have n such data points. So in that, you can have first and second and third and so on. Yi is that is the ith data point. Xij is the value of the jth predictor for the ith observation. Okay, beta naught and beta j's are the intercept and the coefficient of estimates, and epsilon I is the error term. So what is the goal here? So in terms of your optimization problem, again we want to minimize the sum of squared. So for the multiple regression case, the goal is again to minimize the RSS, that is the residual sum of square. So RSS in this case is defined by similar to what we defined for the simple linear regression. So we have n points. Yi minus beta naught cap minus summation j is equal to 1 to n beta cap j xij, the whole square. So very similar to what we had for the simple linear regression case. This was what we had, and now we have it in terms of multiple independent variables. But here, instead of keeping them in terms of equations only and then trying to minimize, it becomes very complex. So you express this equation in terms of matrix form to handle many independent variables. So model is represented in this compact matrix form, which is given by y is equal to x beta plus epsilon. So here y is your m cross 1 vector. Okay, x is your n cross p plus 1 independent variables. Beta is your p plus 1. Why this p plus 1? Because you have that one for all ones for the intercept, and the rest are the values of the x1, x2, etc. Then you have beta is a p plus 1 by 1 coefficient vector, and epsilon is the n cross 1 error vector. So from your least squares, you wish to minimize this residual sum of squares, which again can be expressed in form of your matrix. So that becomes y minus x beta the whole transpose times y minus x beta. So this is how you can represent. So when you open it up, you will get the same summation back. Okay, the same series. So now when we are trying to minimize this RSS, what do we have to do? We have to again take the derivative, take the derivative of the RSS um, with respect to every beta. And since we are representing it in terms of matrix, we can take the uh, derivative in terms, I mean, we can write it in terms of matrix only. Otherwise, you can take the derivative with respect to every beta from here and then express it in terms of the matrix notation. So you will get this. This will give us, by after equating this entire thing to 0, this will give us the estimation of the parameter beta cap as x transpose x, the whole inverse x transpose y. So using the first order optimization, the what you say, the necessary condition for the single variable function to have a critical point, that is, you set the uh, first derivative to 0, or in case of multivariable, you set the first partial derivative to 0 with respect to every variable, you get the values of the estimates. So in this case, you got beta cap to be x transpose x, the whole inverse x transpose y, and in the other case, you got b1 cap to be this. So this is the explicit closed form formulae. So many a times what happens when the data is sparse or data is not so good, it is not easy to find the inverse of such a data always. Inverse may not exist always. So in that case, the least square estimation fails. So in that case, you have other optimization techniques, that is to minimize the RSS, that is the most commonly used is the gradient descent, which we will see in the upcoming sessions. So and these results of multiple linear regression again follow the assumptions that the linear regression, simple linear regression, was following, that is linearity, independence between the observations, homoscedasticity, that is a constant variation or variance of errors, no perfect multicollinearity, and the normal distribution of the error. So now let us look at a few numerical examples using what we have studied. So we will take up the simple linear regression example first. So using the closed form solutions, it is very, very easy to compute the estimator's value, and that will give us the best fit. So these are the data points. You have 5 data points and you have the y for that. uh, so you take the mean of x and the mean of y, you find the difference between them, and then using the formula, so you will require what all you require in the formula, that is x minus x bar, y minus y bar, and x minus x bar the whole square. This is what we derived in the simple linear regression case. So from the data, we can calculate all of it, substitute here, and we get the slope, that is the slope at which we will get the best fitting line. And once we have the slope, we can find out the intercept by substituting it. So that is y bar minus b1 x bar. You have y bar, we have x bar, and we just substitute b1 from the previous calculation, and we find b naught to be 3. So b1 and b naught, these values are the values that are minimizing the residual sum of squares to give us the best fit line. So that is 3 plus 2x, and it looks like this between the data. Another example is with 3 independent variables. So in this case, you have the data looking like this. You have number of observations are 4. So you have y1 to be 10, y2 to be 12, y3 to be 13, and y4 to be 15. So for each observation, you have uh, three independent variables. And this is the y matrix. This is the x matrix with the first column for the intercept. And as per the formula, we required to find the x transpose times x using the matrix multiplication. Then we compute the x transpose y, and finally what we had derived from our first derivative rule, that beta cap to be x transpose x the whole inverse x transpose y. So using that, we find the beta cap estimations of all the parameters, and using these parameters, we find our best fitting line, that is 5 plus x1, and you don't have any contribution of x2 and x3 in predicting the y value. Okay, why is this so? You can already see in the x matrix that your x2 and x3 are very well dependent on x1. So you can get your x2 by uh, just simply adding 3 to all the values of x1. So basically x2 is x1 plus x3. And similarly, you can get x3 is equal to x1 plus 1. So they're not following the multicollinearity rule. They are quite collinear. So that is why their contribution is also not there. So x1 is the only independent variable which contributes in the prediction of your uh, dependent variable y. Okay, so this is another interpretation of your linear regression, wherein you can find the contributions of different independent variables on your dependent variable. Okay, so now this can be done in Excel also. If we have more data, then we can perform this entire analysis in Excel. So this is an example. This is the data for house price and the square feet. So the entire task is to predict the house price given the square feet. So the price is in dollars. And how to do it in Excel? In the data tab, you can click the data analysis button and then select regression, and then you can give your range value. So in this case, you have a the square feet, x y range is b2 to b11. You will select it, and for the x range, that is the square feet, so it is a2 to a11. So you should be very very clear on which is your dependent variable and which is your independent variable. Okay, so in this case, we want to predict the house price. So naturally, our dependent variable is the house price, that is y. And then when you click on the OK button, after selecting the output options, whether you need the output in the same worksheet or the new workbook and so on, you get the output something like this. So we will with the uh, with so many tables. So we will come to all of it one by one. So as of now, we will see that your intercept, the coefficients are given at the bottom of the table, as the intercept is given as 98.248. uh, you can decide with how many significant figures you want to move to, and square feet is given to be, that is the slope is given to be 0.10976. So this is the perfect best fitting line equation, and this is the Excel output. So the key takeaways in this entire table is that the R squared. So you see the R squared here. So it is around 0.581. Okay, so that means the R squared, by now you know what is it, but what is its significance? So basically, it is explaining the variability. So in this case, 58% of the variability is given, is what R squared is telling. That is, your model, this model that you have got the best fitting line, is explaining 58% of variability. Okay, so what that is, I will come to it in short time. So overall model is also statistically significant. Why? Because your F value is 11.08 with a P value very less, 0.01. So I will come to it a little later. And square foot. So this square foot, uh, is also statistically significant predictor. As what does it mean by using, I mean, looking at this line, you can say that it meaningfully contributes to the predicting the dependent variable. You have its value, some value you have got, but is it meaningfully calculating, is this contribution significant, statistically significant? That is given here using the p value, which is very less for the square fit. Whereas for the intercept, it is not very significant, but otherwise also intercept is the value for which your x is 0. So you cannot have any x to be 0 in this case. It is out of your domain, so that doesn't matter. So it is okay. So I'll come to this output a little later. So now let us see what does the uh, what does the r squared variability, how does it show? So this is the scatter plot, and this is the best fitting line of this equation that we have got as the output. And interpretation, we have already seen that um, uh, if you, I mean, the what do you say, that if your b1 is 0.11, that indicates that on an average, if your with every additional or the every unit square foot, the size, I mean, the cost of the house is increasing in $109.77. Okay, so this is how you can interpret this result also. Okay, so another way of interpreting the result is that we can predict the value for the variable which is not in your data point. For example, for 2000, supposing if you want to predict the price for a house which is having 2000 square feet, then you can just look at the graph, or you can just use the equation, put the value of x to be 2000 in the equation and get the y value, which will give you the house price. On the contrary, you cannot predict a value which is outside of this range. Okay, that will be wrong. That is not the extrapolation is not the purpose of this entire linear regression. That is why the spread of the disease in during COVID-19, uh, the linear regression was not applied to it. Okay, so there are other models for it. Okay, so now we look at the variations. Okay, so now let us try to understand how well the regression model fits the data by splitting the total variation into two parts. So um, first is your total, that is the total sum of squares. Okay, so it measures the total variation in the dependent variable y from its mean. Okay, it tells you how much the observed values deviate from the average. Okay, so this is the total variability in your dependent variable before fitting any model. Next comes the SSR, that is regression sum of squares. So it measures how much of the total variation in your dependent variable is explained by the regression model. That is, it compares the predicted value, that is yi hat, with the mean y bar. Okay, and finally we have the error sum of squares. So this measures how much of total variation is not explained by the model, that is residuals of or errors. So this we have already seen. So it compares the actual y value with the predicted values. So this is the part which the model has not explained, and this is the part which model has explained. Okay, so the total is the explained as plus the unexplained variation. Okay, so why this is very important, why these terms are very important? Because this is the basis for your r squared. Okay, which is the fraction of your ssr and sst. That is the fraction of how much variation is explained by your model divided by the total variation. So this can be written as 1 minus sse divided by sst. Okay, So this is a critical formula. This entire breakdown is critical for evaluating the model performance using the metrics r squared or adjusted r square. Okay. So when this r square value, it always lies between 0 and 1 because it is a square one. So for example, let us see how does it affect. Okay, so for example, you consider a random sample of some n employees, and you want to predict their salary with the amount of experience they have. So this is the scatter plot, and this is the fitted line. So what r square will tell, as per the formula, it was 1 minus sse upon sst. That is the 1 minus the proportion of the variation that is not explained by the model divided by the variation, total variation. Okay. So r square basically will tell us how much of the variation in the salary of an employee can be explained by the help of experience. Okay. So r squared is 1 minus sse upon sst. That is, you take the LCM, you'll get it as variation of the mean minus variation of fit divided by variation of mean. So if you cross check these formulas from here, you will get the same thing. Okay, so the little bit of math you can do, which is very basic, and you will get these. So what we do is we first try to see the variation of mean, give different values to variation of fit, and then see what is r square telling us. So for example, if your variation of mean is 11.1 and variation of fit is 4.4, then what is our r square? It is 0.6. So that means this is the variation of mean, that is 11.1, and this is the variation of fit, and together they are giving us r square. So that means experience of an employee explains 60% of the variation in the salary of the employee. Okay. Next is, if we put the variation of fit to be 0, that is all the data points are nicely lying uh, on the line. So in that case, your r square becomes 1. That means experience of an employee explains 100% of the variation in the salary of the employee. Okay. Finally, if we have both the values as same, that is variation of mean and variation of fit, then r square is 0. So as you can see from the data, from the visual also, that experience does not of an employee explains no variation in the salary of the employee. Okay. So now consider adding a new variable, say another variable x2 in the same model, the height of the employees, which practically does not impact their salaries. So, but your mathematical linear regression model becomes like this: b0 plus b1 x1 plus b2 x2. So in this case, the least square method, what it will do is it will ignore this parameter. This is how the method is designed. As we saw in the example also, in the numerical example previously, where your x2 and x3 did not contribute anything to it. So this will ignore. So this way linear regression is robust to irrelevant variables. And in this case, instead of a line, you will have a plane as the separating, uh, as the as the best fit to the variables. So least squares automatically assigns low weights to the variables that don't contribute, and this makes the model very reliable. So this doesn't mean that we keep on adding the irrelevant factors also, because it adds on to the model complexity and the computational cost. So in practice, these irrelevant predictors can be detected and removed using the p values also. Okay, so in case you have many factors, many independent variables, then you can see the p values, as I demonstrated in my first lecture of evaluation metrics, where you can see, check the p values and select only those features which are having less p values for the model. Okay. So now we come to the r square values. So if it is 1, then you have a perfect linear relation, as we saw. If it is 0, no linear relation. And if it is lying between 0 and 1, you have a weaker linear relation. That means some but not all of your y variation is explained by the x variation, as we saw in the example of excel, in which we were predicting the house prices. You had only 58% variation explained by the uh, square feet. So the the remaining 42% is not explained by your model. So that may be some other factors like the proximity to the school, or proximity um, uh, to shopping complex, and so many things which your model is not explaining. So now we come to the statistical significance of this r square. So as so far we have seen that r square tells us the variability. I mean, how well the independent variable explains the variability in the dependent variable. And if the value is high, then it indicates a strong fit. But is this fit statistically meaningful? That will be uh, answered using the p value. Okay, so p value is calculated using the f test, which will help us determine whether the obtained r square is likely due to chance only, or it has is it actually significant. Is it actually telling us the variability? Okay, so a low p value is generally shows the model significant, and the relationship between the variables is statistically valid if you have got low p value. Together, the r square value and the p value provide a complete picture of model performance and reliability. Now, let us look at the f test with which this p value is calculated. So f test basically, this formula gives us the f test statistic. Okay, so with this formula, with the value of this f, it is the statistic, uh, uh, that is the parameter that we are uh, finding. Okay, so this is used in the multiple linear regression to assess the overall significance of the regression model. So that is whether at least one of the independent variables significantly predicts the dependent variable or not. So the formula here is MSR upon MSE. So what is this MSR? It is the mean squared regression. Okay, it is the mean squared regression. That is your regression sum of square divided by the number of independent variables. Okay, so this is the regression sum of squared divided by the independent variables. So what is this SSR? We've already seen it. That is variation explained by the model. Okay. Then we have the MSE, which is SSE upon n minus k minus 1. So what is this SSE? That is error sum of squared. That is unexplained variation. That is the difference between your predicted and the actual value, divided by n minus k minus 1. So n is the number of observations in your data, and k is the number of independent variables. Okay, so this is your f statistic formula, and this f follows the f distribution with k numerator degrees of freedom and n minus k minus 1 denominator degrees of freedom. So f table, if any of you have seen, f table is basically having 2 degrees of freedom. So you have to always look for this f value corresponding to 2 degrees of freedom always. Those are the statistical tables that people have already found out for our ease, which will help us to find the p value. So a high f value, what does it mean? High f value means this MSR is much larger than MSE. That means the model explains a significant portion of variation in your uh, dependent variable. That means the model is statistically significant. If your f value is low, that means both these are kind of equal. So what happens? Predictors do not explain much variation. Every predictor is having very less contribution, and they do not actually explain uh, the uh, the variation in the independent variable, and the model is not statistically significant. So this is how the f statistic, f test for significance works. So now let us come back to the Excel output that we had got. So in this, we had got the r squared value to be 0.58. So now we know that what is r squared. It is giving us the variability that your independent variable is explaining for the dependent variable. So in this case, it is 58.1%. um, then you have the multiple r. So this is basically the correlation coefficient, okay, between the observed and the predicted values. So 0.76 is basically predicting moderately strong positive correlation. Then you have the adjusted r square values. So this is for the number of predictors. This is basically useful when you are comparing models with different numbers of predictors. Then you have the standard error, which is kind of the standard deviation. Okay, typical, this is the standard deviation of your residuals. And then you have the observations, that is 10. And then you have this test, f statistic, that is there. This is giving us the uh, model as a whole, whether it is statistically significant or not. So this part of the output is telling us that. So df is giving us the degrees of freedom. For regression it is 1, for residual it is 8. So k, for if you remember in our previous slide, you had the msr, that is regression, mean squared regression, with k degrees of freedom. So in our example, we had only one independent variable, so you have the degrees of freedom to be 1. And for residual, that is msc, it is n minus k minus 1. So we have 10 observation, minus 1 minus 1, which is 8. Okay, so this is 8, and you have the total degrees of freedom to be 9. Then you have the sum of the squared. So sum of the squared is how much variation is explained. For regression it is this, and unexplained, that is for residual, it is this, and the total is this. Mean sum of squared is what is useful in calculating the f statistic. So mean sum of squared is this for regression, and mean sum of squared is this for residual. So if you divide these two, you will get 11.08. That is the f value. And if you look at this value corresponding to 1 and 8 degrees of freedom in the f distribution table, it will give you the value as 0.010. So that is very less than 0.05. That is at 5% significance level. You can say that the model is statistically significant, and your square fit is contributing meaningfully to, it is contributing already because we have got the value, but it is contributing meaningfully, statistically significant to the entire prediction. Okay. uh, Now, so as I had already explained in the evaluation metrics slide, how this all these things work is that any hypothesis testing works is you need to come up with a hypothesis testing, null hypothesis and alternate hypothesis. In this case, your null hypothesis is that your slope is equal to 0, and alternating hypothesis is it's not equal to 0. So we are choosing the significance level to be 0.05. That is the uh, value for which we look at the f, for which we look at the f value in the probability, f distribution table. And this is the threshold that we set for the obtained value. So this is kind of saying that the probability that your b1 is equal to 0 is 0.05. 0.05. So that is 5%. If the chance that B1 is equal to 0 is less than 0.05, that is, it is less than 50%, then what do you say? You accept the the null hypothesis. So this is the whole idea of setting the threshold and looking at the p-value, and then making the conclusion. So graphically, so F distribution follows a graph like this, okay, and you set the threshold at 0.05. So as we saw in the previous output, that your F value is 11.08, which is greater than this 5.32. So it is uh, above this threshold. Okay, at this threshold the F value is 5.32, but what we are getting is 11.08. So our F statistic value is falling in the rejection region, or it is also called critical region, and therefore we have to reject the null hypothesis and say that your slope is actually not equal to 0, and we have already got its value to be 0.11, this one. Okay. Then we also have the third part of the table, which is from the t-test. So we will look at it one by one. So this is about the R squared, which is showing 58.08% variation in house prices, explained by the variation in square feet. We have seen about this F statistic. It is the division of MSR and MSE. Now we will look at this table, this part of the output. So standard error also I have covered. So okay, so now we come to the t-test for the slope. So what we are trying to do with this t-test is that we want to see whether the relation between x and y is linear or not. So that is your beta 1 is 0 and beta 1 is not equal to 0. So linear beta 1, if it is 0, then there is no relation. If it is not equal to 0, then linear relation exists. So so your test statistic, the formula for t test statistic, just as we had for f test statistic, is the difference between uh, actual b1 uh, minus what we hypothesized divided by the standard error, and the degrees of freedom is n minus 2. So where n minus 2, why n minus 2? N is the number of observation, and 2 because we are having two estimators, that is b1 and b naught, that we are trying to estimate using this. So that is the number here. So b1 is the regression slope coefficient, and beta 1 is the hypothesized slope, that we are hypothesizing it as 0, indicating that there is no linear relation, and this is the standard error which we got in our output. So again, we take the same example of house price and square feet, and this is our estimated regression equation, and the output is this. So you can see from here what our best slope is 0.109. How much it is different from 0, that we are checking. So we will put it in the formula, that is the obtained slope minus what we hypothesize, that it is equal to 0, divided by the standard error that we had, which is 0.03297. So this is the standard error for the square feet that we are putting, and we get the t value to be 3.329. So again, the same procedure follows here. You have to set a significance level. Usually it is 0.05, that is 5% significance level. And this test is a two-tailed test, because we are not saying that the hypothesized slope is greater than 0 or less than 0, we are just saying that it is different, okay, from 0. So this is a two-tailed test. So this matters in the t-test because the value of t that we need to find out from the table depends on whether your test is a two-tailed or a one-tailed test, okay. uh, so t statistic is this, and degrees of freedom, again the table of value, the t distribution table value will give you the t statistic value for a particular degree of freedom. So in this case there is only one degree of freedom, whereas in f test you had two degrees of freedom. So for us, it is 3.32 obtained, and from the table, you get the t value at 0.025 because it is a two-tailed test. So you split your 0.05 in two, that is 0.025 and 0.025, and look at its value for 8 degrees of freedom. You will find it to be 2.30, which is less than what we have observed. So our found value of t falls in the critical region again. So we must reject the null hypothesis and say that your hypothesized slope is not equal to 0, indicating that there is a linear relation between x and the y. There is sufficient evidence to show this. So this is how the t-test works, and this is how your last part of the output tells you. So this is the p-value for t statistic of 3.32, which is less than 0.05, and therefore we reject the uh, null hypothesis, saying that there is sufficient evidence that the square footage affects the house price. So further, we can also present the result using the confidence interval, which is given by B1 or whichever parameter that you're finding, plus or minus the t value at n minus 2 degrees of freedom for this much standard error. Um, so that this is the confidence interval for intercept. It is the lowest value that the intercept can take is minus 35.5, and the highest value with 95% confidence interval is 232.07, okay. And for the square fit, whatever we have predicted a value of 0.11. So the lowest that we can have, this value is valid in this interval, that is with 95% confidence interval. We can say that we can say that the lowest that the slope can be is 0.033, and the highest the slope can be is 0.185. So this is the confidence interval. So this is all about the Excel output. And finally, you have these inferences. Since the units of house price variable is in dollars, you are 95% confident that the mean change in sales price is between $33.74 and $185.8 per square foot of the house size. And this 95% confidence interval does not include 0. So there is a significant relationship between house price and square feet at the 5% level of significance. Similarly, you can run a t-test for correlation coefficient also, saying that there is no correlation between x and y, and there is a correlation. So in this case, the formula is again almost the same as what we saw in the previous case, and then you can get the value as 3.3, which is greater than 2.3. So you reject the null hypothesis and say that there is a correlation. There is evidence of a linear association between square feet and house price at 5%. So you can increase this level of significance to 10%, or you can decrease this level of significance to 2% or 1% to be more precise. So you're accordingly your t value here will change. Same goes with the case of f value also. You can decrease or increase the level of significance depending on what precision you require. So this is about the linear regression. And what we learned has been summarized in this slide, that we tried to understand the relation between dependent and independent variables. We saw the practical interpretations of the slope and the various slopes and the intercepts in the line, and how adding irrelevant variables does not up, in, does not affect the model, the reliability of the model. And once we get the r square values, how the p values are used to see the significance, statistical significance of these r square values, how you can use f test and t test to help say more about the model in terms of reliability conclusions and the statistical significance conclusion. So, any questions? I am